So welcome to lecture 4 of Digital Systems 1. These lectures will be offered in 5 parts from part 0 to part 4. The contents of lecture 4 would cover chapter 3 of our recommended textbook, which is the Digital Fundamentals by Thomas Floyd. So in chapter 3, we're going to cover logic gates. And for each logic gate, we're going to look at the symbol, the operation, truth table, logic expression, waveforms, and applications. The logic gates which we are going to focus on are the inverter or NOT gate, AND gate, OR gate, NAND gate, NOR, XOR and XNOR gate. Apart from that, we are going to look at the application of these logic gates, their waveforms. Then we'll move on to fixed function logic ICs. We'll look at the naming and packaging. In particular, we'll look at the different properties of these fixed function logic IC integrated circuits. We'll look at propagation delay, power dissipation, speed power product, and the fan out. In the book, we shall only cover sections 3.1 to 3.6 and 3.8, which means sections 3-7 and section 3.9 are not covered. All announcements about the tests are going to be placed on Vutela. Test 2, that's going to come to evaluate this lecture notes, is going to cover both chapters 4 and 5 of the recommended books. Now, as I previously stated, we are going to look at each of these gates, and the student is expected to be able to identify a logic gate using its symbol, to be able to describe the operation of a logic gate, to be able to draw the truth table of a logic gate, that is to understand the operation of a logic gate, to be able to sketch also a timing diagram of a logic gate, that is to indicate a waveform, how given a certain input in form of a waveform, how the logic gate will behave. The student is also expected to write an expression, a logic expression in Boolean algebra for a particular logic gate, and is also expected to describe how a logic gate can be used in a certain application. The first gate, the simplest of them all, is the NOT gate, or what's commonly termed an inverter. The NOT gate has this triangular symbol with a small bubble in front, and the other alternative symbol, the IEEE symbol, it's as shown here. So the way the logic gate simply operates is it inverts the logic. It gives us the output is the opposite of the input, which means if the input is a 0, then the output will be a 1. If the input, on the other hand, is a 1, then the output will be a 0. And it's represented by a bar. What do I mean by a bar? I mean this notation. So the output is the input bar. So X is equal to A bar if X is the input. So in terms of the truth table, this would be the truth table, which means if the input is 0, then the output becomes 1. When the input is 1, the output becomes 0. If you look at the timing diagram, if this was the input, how the input behaves, moving from 1 to 0, back to 1, and so on and so forth, then it means the output will simply do the opposite. It will be 0 and then 1. The simplest application of an inverter would be to look at the way the thermostat operates. So a thermostat, or a heating element of a heater, will be controlled such that in the thermostat you may set a certain temperature. Say you set 20 degrees Celsius, which means the heater will heat the room up until it reaches a level of 20 degrees Celsius. So the logic of the that digital thermostat will behave like an inverter. So it will simply detect if the temperature in the room is above 20 degrees. If it's below 20 degrees, if the temperature is below 20 degrees, represented by logic 0, it will turn on the heater. Whenever the temperature goes above 20 degrees, which means the input is 1, then it will turn off the heater. So this would be a simple example of how the NOT logic gate works. So the next logic gate to study is the AND gate. And the AND gate has this IEEE symbol, which is a box and an ampersand symbol, or it has the symbol shown, which is a convex front and a straight at the back. The way the AND logic gate behaves is if all inputs are high, then the output is going to be high. Otherwise, the output remains 0, as you can see in these 3 examples. The expression for the AND gate is if the inputs are A and B, then the output will simply be A dot B, or simply A multiplied by B. The next gate is the OR gate. The OR gate is represented by the logic expression plus, which means if these are the inputs, then X, the output is going to be A plus B, which is just simply read as A or B. So the 2 symbols will be this symbol, and the IEEE symbol will be greater or equal to 1, which simply means, in fact, this IEEE symbol explains the truth table of the OR gate. The OR gate's output is 1 whenever at least one of the outputs is high. Otherwise, it's going to be 0. The next gate is the NAND gate, or the negative AND gate. So the way the NAND gate is made is it's like an AND gate with a bubble. The bubble simply means it inverts the output. So the symbol for the AND gate, for the NAND gate, would be like that, or this way. So the way it operates like an AND gate plus a NOT gate towards the end. So it simply does the opposite of the AND gate, in the sense that the output is high if not all inputs are high. Okay. So go back to the AND gate and compare. You will see it does the opposite. The next gate is the NOR gate. The NOR gate is opposite of an OR gate. It has this and that symbol. It's like an OR gate with a bubble in front, an OR gate plus a NOT gate. And it operates as the opposite of the OR gate, which means the OR gate, the output is high whenever all inputs are 0. And there are multiple notations which you will later learn in chapter 5 of the OR gate, multiple symbols. It can sometimes be called a negative AND gate and have that particular symbol, but that's for later on. The next one, which will be interesting in terms of applications of arithmetic circuits, is called an XOR gate, an exclusive OR gate in full. So an exclusive OR gate is like an OR gate with a small ring at the back, as you can see, or it's equal, it has a box, the IEEE symbol will be a box with an equals to 1, which means the output of the XOR gate is 1 only when exactly one of these outputs is high. In this case, if he has a 2 input. And the expression for the OR gate is the exclusive OR gate. It's a plus with a circle around it, which then is equivalent to this following expression. So the last of these gates is called an exclusive NOR gate. An exclusive NOR gate is like an exclusive OR gate, but with a small bubble in front. So it's a negation of an exclusive OR gate. The other type of symbol is this IEEE symbol with that small triangle in front, which shows it has an inversion. So the output of an XNOR will simply be the output, the opposite of a XOR gate, as you can see in this table.